So what we started doing on Friday was to start with what we call the model-based framework. So what Angela did during the first week was to cover what we call the design-based framework, and now we are moving to effectively covering the model-based framework. And the first set of models that we decided to introduce is basically what we call the area level models. Okay. So the most famous area level model, the one that has been used widespread, used in wide set of applications, is the Fairhead model, and this is what I started presenting on Friday. The Fairhead model is based on what we call a random effects model or a mixed effects model, and it comprises two parts. So in the first part, the model is you define a sampling model, which relates basically the direct estimator of the parameter of interest, which here we denote by theta hat I, and we use a superscript direct to indicate that these are direct estimates, and these are design unbiased estimates of what we're trying to measure, and we relate that to the true population parameter theta I, and of course we know that around the direct estimate there will be some sampling variability that is associated with the direct, because obviously we don't see the entire population, but we have selected a sample, a probability sample from that population. So the EI here is what denotes a sampling error. Okay, the direct estimate can be any of the estimators, can be calculated, computed under any of the estimators that you have seen with Angela in the previous session. It can be a Horowitz-Thompson estimator or a Hayek-Brewer estimator, and in this case we assume that we have M area. So effectively, the area level model is applied to, in order to apply the area level model, as we will see later today, what you need to have is one observation per area. So you need the direct estimates of what you're measuring for each of the areas, and then you need observations on a set of covariates, and these observations are also defined at the area level. Okay, so that defines a sampling model, and then there is a second part of the model which is called the linking model, and in the linking model what you do is you link theta I, you express theta I as a function of a reduced number of explanatory variables, okay, which are denoted by HI and are also defined at the area level. You see that the H's here have only one subscript I. So for each area you have a vector of observations that are associated with the explanatory variables, and these are also then related via a set of regression parameters beta plus an area-specific random effect that I denote by UI here, okay? And the area-specific effects and the sampling errors are assumed to be distributed according to distribution with mean zero and variance sigma squared U, that is the between area variability, and EI is associated with a variance sigma squared EI, and this is basically the sampling variance. So we have two models. We have a sampling model, we have a linking model, and then we put the two things together. And you can see that if you look into the combined model, what you have is a regression model, effectively, that has on the left-hand side the direct estimates of what you are measuring. On the right-hand side, you have the set of explanatory variables and the set of regression parameters beta plus the random effect plus the sampling error. Okay. And here is where we started talking about what is known as the best linear unbiased predictor. So we want to find a predictor that is best in some respects, and that that predictor, the best linear unbiased predictor here, is defined as I define here in this expression, the theta hat I blob, the best linear unbiased predictor of your parameter of interest in area I, is nothing more than a combination, right, between the direct estimate and the regression synthetic estimate. So is a combination that depends on weights gamma I, okay, and the gamma I is effectively what we call the shrinkage factor. So gamma I is weighting the direct estimates, and 1 minus gamma I is weighting the regression synthetic estimate. Okay, so what we want to do here, if you think about it, you say, I know I want to find a best estimator of my parameter of interest theta I by making the best use of two things. One is my direct estimates, okay, which is what I directly observe from my sample data in each area. And the other is effectively all the other data that are available in my survey, okay, and in the auxiliary information. And the question is how to make best use of this. So how to decide the weights, gamma I, okay? And the weights will depend, the gamma I, as we will see in a moment, depends on both sigma squared T, the variance of the direct, and also on sigma squared U, the between area variability. Okay, so, but for now, what I want you to see, which is in contrast to what you saw before with direct estimates, is that the blob is trying to combine two parts of the data, two pieces of information. One is the direct information, and one is the regression synthetic information that comes by the use of the model. Okay, so let's look again at how this blob looks like. Okay, and what you need to realize here is, obviously, if I have direct estimates that are very reliable, then I'm going to give higher weight to the direct estimates, because if I have good direct estimates, then I'm okay with that. They're having this. The direct estimates have good properties. They are design unbiased, okay. And so if they have also low variance, then I'm happy with these estimates, okay. So if my direct estimates are reliable, okay, what do we mean by reliability here? One way to define that is if you have direct estimates that have low sampling variance, then obviously you should be giving a higher weight to the direct. If, on the other hand, your direct estimates are not very reliable, then gamma I will be small, 1 minus gamma I will be bigger, and then the second part that basically relies more on data from all areas, okay, and on the regression coefficient beta hat will be given a higher weight, okay. And the blob can be also written in the form of a mixed model. So the best linear unbiased predictor of theta I is nothing more than X transpose beta hat plus UI hat, okay? And this UI hat here is the difference between the direct estimates and the fitted values under the model. So it's taking theta I hat direct minus XI transpose beta hat. You see that this is like a residual, okay, and then you weight these residuals by gamma I, okay. So effectively, that's effectively what gives you the predicted random effect UI. So the predicted random effect is nothing more than a residual weighted by a factor gamma I. What is gamma I? Gamma I, as I said, is called the shrinkage factor, because this will decide how much you will go to the balance, the trade-off between going fully to the direct estimates or going more into the regression synthetic estimate, okay? So if you give more weight to the regression synthetic estimate, then what you tend to do is you shrink more compared to the case where you give more weight to the direct estimate, okay? And this will depend on two parameters. It will depend on sigma squared U, and it will depend on sigma squared EI, okay, on the sampling variance, which is denoted by sigma squared EI, and also on the between area variance, which is denoted by sigma squared U. So just to see a bit more what does this mean, one good thing to start doing now is to calculate the mean squared error of the blob, okay? Remember that in the blob, we have not estimated yet, we have not done anything about sigma squared U. We assume that sigma squared U is known, okay? So if we take the MSC mean squared error of the blob, so if you take the mean squared error of this expression here, right? So, and you go through the algebra, which I'm not showing here, then you will end up basically that the MSE is equal to the variance of the blob because of the unbiasedness property under the model. So the mean squared error will be equal to the variance, and the variance of the blob, excuse me, will be equal to this expression. So it will consist of two parts. One part is gamma I times the sampling variance, sigma squared EI, and the other part is 1 minus gamma I squared. And then you have this expression here, which is H transpose variance of beta hat times Xi. So you see that there are two ingredients that contribute to the variance of the blob. One is the sampling variance, so that's the variance of the direct, plus the variance of the estimated regression coefficients, okay? And we denote that by G1i and G2i. So these are generic expressions for these two terms, okay? Now, if I have a very large number of areas, so if my M goes to infinity, the number of areas goes to infinity, then this second part, the G2i, will become small, okay, because my betas will be estimated more and more reliably because my number of observations is increasing, okay, and the leading term will be purely the first term that depends on the sampling variance of the direct. Okay, and you see that because G1i is equal to gamma I times sigma squared EI, then this is much less, or less definitely, than sigma squared EI, okay, because you know that gamma I is between 0 and 1. So that tells me that the variance of the blob under the model, okay, is gamma I times sigma squared EI, and this will be less than the variance of the direct estimate, okay? And that illustrates the superiority of using a model over the direct, especially when the model has been built in such a way where the between area variability that remains unexplained after controlling for the explanatory variable. So I want my sigma squared U to be as small as possible, okay? And if I achieve that by finding good predictors from your data, it may be admin data, it may be geospatial data. I want to find good predictive predictors to reduce my unexplained between area variability. And if I'm able to do that, then that will lead in superior performance of the model over the direct estimates, okay? So I think it is important to try and reflect a bit on that. I don't want you to hang on too much on the detail of it, on the mathematical detail, but I want you to understand the intuition, right? So you see that the blob is a combination between two things, the direct estimates and then the regression synthetic estimates. And the game there is to try and find the best combination of these two. The best combination depends on the shrinkage factor, and this shrinkage factor is what will determine how much weight I give to my direct estimates and how much weight I give to my regression synthetic estimate. At the moment, I'm talking about blobs, so I have not assumed that we have found a way to estimate sigma squared U, the sigma U, okay? Obviously, when it comes to actually fitting the model, then we have to find a way to estimate the between area variance component, so the sigma U, the sigma squared U. So that takes us effectively from the blob to the E-blob, okay? So up to now, we assume that sigma squared EI and sigma squared U are known. Of course, with the data we have, it is impossible to estimate both variance components because we have access to only area level data, okay? So we have one observation per area, okay? So what we do for the Fairhead model, we assume that sigma squared EI, so the variances of the direct are known, okay? And what we do is we estimate with our data sigma squared U. And sigma squared U, to be estimated, there are multiple ways to do that, and the literature describes a lot of ways. I'm giving you 3 possible ways of estimating sigma squared U. One is to use maximum likelihood estimation. The other is to use residual maximum, restricted maximum likelihood estimation, residual maximum likelihood estimation, and the third one is to use a method of moments estimator. Okay, but effectively, once you have estimates of sigma squared u, so if you replace sigma squared u by sigma hat u, effectively, so you have sigma hat u, you have beta hat, and you assume that the variances of the direct estimates are fixed, that will lead you to what we call theta hat I EBLAP, and EBLAP stands for empirical best linear unbiased predictor. Okay, so we go from a BLAP to an empirical EBLAP because we have used an estimation method in order to figure out the likely value of the between area variability, sigma squared u. Okay, so I'm going to stop here, and what I want from you is to ask you if you have any questions about the logic of this model, the logic of the area level model. So we have an area level model, we have one observation per area, effectively, and a set of covariates for each area. We have a sampling model, we have a linking model, and based on that model, we are effectively expressing, find an expression for the best linear unbiased predictor, and then an expression for the empirical best linear unbiased predictor. Do you have any questions before I continue? Okay, I don't see any reaction from here. So I'm going to continue and say that one of the biggest tasks in small area estimation, especially when you go to model-based methods, is to find a way to estimate the uncertainty around the estimates. Okay, so and that leads us to something that has dominated the small area literature for a very long time, and it's still a key area of work, and that is finding appropriate ways of estimating the mean squared error. Okay, so with the Fairhead model, as with all other models that we will see from now on, so in this session and the following session in part 3, for every model that we come across, then there will be a description around possible ways of estimating the mean squared error. Remember that here we are estimating, or we are aiming at estimating national things, parameters that potentially will become national statistics. And because of that, you have to have a well-defined measure of uncertainty that will lead you then to define potentially coefficients of variation and also confidence intervals. So why is this more complicated to estimate the mean squared error in this case? The answer to that is basically what I'm going to describe here. Okay, so a naive way of estimating the mean squared error is basically simply to replace the unknown parameters with estimates. Okay, however, if I do that, then that will ignore the uncertainty due to estimating the parameters. So I want effectively to have an estimator of the uncertainty, an estimator of the mean squared error, which is used as a measure of uncertainty in this case, that captures the uncertainty due to the parameter estimation. Okay, and in order to do that, I have to make assumptions now about the error terms. And the assumption that is going to be introduced here is that I will assume that the area effects, the area random effect, so that's the UI. Remember that I had two parameters here, UI, two error terms, UI and EI, and for both, I'm going to assume that these are normally distributed. So there is an assumption of normality about these error terms. Okay, so if I assume that, then my mean squared error of the EBLAP, remember that what I'm interested in estimating is the mean squared error of the empirical best linear unbiased predictor. This is the predictor that now it has replaced the quantities that I assumed known with estimates of this quantity. And I want to capture this uncertainty around the estimation of these quantities. So how can I define the mean squared error? The mean squared error is nothing more than the expected value of theta hat I EBLAP minus the true value theta I squared. And this can be decomposed into two parts. One is the expected value of theta I BLAP minus theta I, so that's the uncertainty around the BLAP, plus the expected value of theta hat I E blap minus theta hat I blap. So that's basically the additional variability that comes in as a result of moving from my blap to the E blap. So as a result of estimating the model parameters. Now, if you look into this expression, the first part is nothing more than the variance of Blob, and we know that the variance of Blob is basically comprises two terms, the G1 term and the G2 term, which I defined just before. So it's this thing here. So in order to calculate that, you don't need a lot. You need the gamma i's, you need the direct variances, and then you need also the variance of the beta hats. The variances of the beta hats can be output from any statistical software that fits regression models. So that's pretty straightforward to do. What is the most difficult bit to get is the third bit. Okay, so it's the expected value of the theta hat I blap minus the theta hat I blap squared. And I will denote that by a term called G3 here. Okay, so this is a G3 term. And what I want to find now is an estimator of this mean squared error. Okay, now a lot has been said about these estimators. Okay, and thankfully we have thanks to the work of people in the past, we have analytic mean squared error estimators. So that means for certain models and for certain target parameters, you don't need to rely on computer-intensive methods like Bootstrap and Jackknife to estimate the mean squared error. Okay, so one of the most famous estimators that has been proposed, say under the Fairhead model, is analytic estimators, is the so-called Persadra estimator. Okay, and the Persadra estimator is defined in the simplest case as follows. So you say that the estimated mean squared error, so you see that now I have included the hat on top of the mean squared error, is equal to G1, and then I have replaced sigma u by sigma squared hat, because this is estimated now, plus G2, and then plus an expression, plus 2 times an expression for G3. And the G3 purely depends on this expression here. So you see that the G3 term is a function of the sampling variances of the directs. It's a function of the estimated between area variability, this sigma squared u, and also an estimated variance of sigma squared u as well. And this last bit here, the variance, will depend on what method you use to estimate sigma u. So depending on whether you use maximum likelihood or residual maximum likelihood of method of moments, there will be a different expression. So that is an analytic mean squared error estimator. If you want to find out about this estimator, you can download and read the seminal paper by Prasad and Rao. It's a paper that was published in the Journal of the American Statistical Association, and will describe mean squared error both under the area level model and later, as we will see, under the unit level model as well. The good news is that you don't need to worry about all these expressions. I'm just describing this in quite high level terms. I'm not, obviously there's a lot of algebra and mathematics going behind this expression. The mean squared error depends on a Taylor linearization approach to obtaining this estimator. However, all of this has been programmed into statistical software, and you have ready-made tools that will allow you to output the estimated mean squared errors, in this case of the Persadra. But one thing I want you to become aware is that this is important because when it comes to estimating the mean squared error under the model, it is very important to realize that you are estimating a mean squared error of an empirical best linear unbiased predictor, and hence you have to capture the variability because of the estimation of the model parameters. Okay, so this is an analytic estimator, and as I said, if we have analytic estimators, that's great, okay, because we can see all the mathematics, we have closed form expressions, and we can use the closed form expressions in order to estimate the uncertainty. However, this is not always possible, there are models that are more complex, or there may be parameters that are particularly complex, and developing analytic mean squared error system estimators becomes very difficult. So how do we solve the problem in this case? In this case, the problem can be solved by using computer-intensive methods or replication methods. And Angela mentioned that I will go through a number of these kind of techniques, with particular emphasis on Bootstrap. Okay, so Bootstrap is one way of estimating uncertainty. If the statistic that we're trying to estimate or the estimation method of the model are particularly difficult to allow us to go with some analytic method, some method of analytically developing a formula that will give us an estimate of that uncertainty. And here we're going to talk about parametric bootstrap. So effectively, what Bootstrap is doing, Bootstrap is trying to replicate the world, the superpopulation or the population or the data generation mechanism that we assume under the model, then select a sample from that world, replicate again a data set, and then with a new data set, what we're going to do is we're going to implement the estimation that we're interested in. And then we're going to repeat this process many times. And at the end of that process, we are able to get a handle on the variability, the uncertainty that is associated with the process, the estimation process that we employ. And we're using the term parametric because here we're going to generate bootstrap samples under the model. So we assume that our model is correct, and we're going to generate estimates of the uncertainty under that model. And that's an important thing to remember, because obviously if your model is not correct, this is not only going to affect your point estimates, but it's also going to affect your estimates of uncertainty, in particular if you assume that your bootstrap is generated under the assumed model. Okay, and that makes the issue around model selection and model building very, very important. So let me go through one of the bootstrap methods. So there are many bootstrap ways. So we have non-parametric bootstraps as well that do not depend on the assumed model. And we have a number of other bootstrap schemes that have been proposed in the small area literature, but also more generically in statistics. But let me go through a bootstrap approach to estimating the mean squared error for the Fairhead model. So the target here is to estimate the uncertainty of the model-based estimates, theta hat I, that we obtain under the Fairhead model, okay, or the empirical best linear unbiased predictors. So here I'm going to use a notation where if I use a star as a superscript, that will denote quantities that are in the bootstrap world. So I have a bootstrap world that I'm going to generate. I don't observe this, but I have a mechanism, right? A device, a stochastic device that is my model, and I'm going to use my model to generate data that look like the data, how the data, my original data has been generated. So I'm playing a bit God here under the model, right? So a star is a bootstrap world quantity, and the superscript B will denote a bootstrap iteration, okay? So how do we start? The process starts basically by fitting the Fairhead model to my data, my survey data, and using also whatever other information I have. And under that process, I'm getting estimates of beta hat and sigma hat, sigma u square hat. So what I do now is I'm going to generate bootstrap quantities. So I'm going to generate a replication, one realization of random effects, which I'm going to denote by UI star. You see now I'm going to use what? I know that I'm assuming that my UI stars follow a normal distribution with mean 0, and variance sigma u square hat. Okay, this is what we estimated with our original data. So under my assumption, right, and having estimated my sigma hat u, I can draw one set of random effects. Okay, what else can I do? I can draw one set of sampling errors, EI star, okay, which is following a normal distribution with mean 0, and variance, the sampling variance that I estimated for the direct estimate. So this is sigma squared EI. Okay. So once I have my U stars, so UI star and EI star, then what I can do is I can generate a bootstrap value of theta I from the linking model. So I'm going back to my linking model, and I'm saying, what is my theta I, my true parameter in the bootstrap world? So what is theta I star? Is nothing more than xi transpose beta hat plus the corresponding drawn random effect, UI star. And also, I can also generate a set of direct estimates in the bootstrap world again from my sampling model. So I want to have one set of direct estimates in the bootstrap world, and this is nothing more than taking theta I star that I generated from my linking model before plus EI star, which is the realization that I explained before. Okay, so with the steps up to step 5, I have generated a new set of bootstrap area level data. So that's another set of data comprising a new set of direct estimates, which are called theta I hat direct star. I have my xi's, my covariates don't change. I have my census data, administrative data, geospatial data. Okay, I have my sampling variance and everything. And what I can do now, I can use my new bootstrap area level data to re-estimate, refit my Fairhead model. And if I refit my Fairhead model, I'm going to get a new set of empirical best linear unbiased predictors with the bootstrap data. You see that the new theta hat i's eBlap has also a star here. Why does it have a star? Because in order to obtain this new set of estimates of eBlaps, I use my bootstrap data, not my original data. Okay, so what I need to do now is I'm going to repeat steps 2 to 6 for a large number of times. So I'm going to 2, regenerate area effects, going to 3, regenerate EI stars, calculate new bootstrap values of theta I, calculate a new set of direct estimates, recalculate my eBlaps, and I'm repeating that for a large number of times. I can run 250 bootstrap samples, 500 bootstrap samples, 1,000 bootstrap samples. But at the end of the day, the naive or one way of calculating the mean squared error, an estimate of the mean squared error of the eBlap, is by doing what? Taking the difference between the eBlaps that you calculate from each of the bootstrap samples, subtracting the true value in the bootstrap, in each bootstrap, squaring that, summing over all the bootstrap samples, and dividing by beta. Okay, so effectively, you are replicating the entire process many times, and at the end of this process, you have a set of estimates that you can use in order to calculate the mean squared error. So to see how much variability there is, how much variable they are, the eBlaps from each of the bootstrap samples are around the true value theta I, and that is a way of measuring the mean squared error. Okay, so this gives you a tool. It's a computational tool that will be used extensively in this course, because as we move to different parts of the course, you will see that for more complex parameters, we will need to use bootstraps. But using bootstrap effectively, you can get some estimates of uncertainty for the eBlaps. There is another seminal paper that you may perhaps have an interest in looking is a paper by Peter Hall and Taps Maiti in 2006, and that is about parametric bootstrap methods for small areas prediction in particular. Okay, and this is a paper that was published in the Journal of the Royal Statistical Society Series B. So it's a very good paper to have a look into and see how the parametric bootstrap ideas is applied to small area prediction. Okay, so one of the things that is really important to remember is that, and I'm going to cover it here for a bit, is that I expect that in the applications that you're going to do in Colombia, then you will face a problem with prediction for out of sample areas. Okay, let me remind you what it means to have an out of sample area. Out of sample areas are areas where you have 0 sample sizes, and from what I understand, in the case of Colombia, there are a number of municipalities that are not in the sample. So that means that your NI, your area-specific sample size, is equal to 0. In this case, you don't have a direct estimate. You can't really compute a direct estimate because you don't have any sample data from that area. So there is nothing you can do with direct estimators. In this case, you really need to rely on some kind of synthetic estimator. And so here is one synthetic estimator you can use. You can use as a synthetic estimator of theta hat I for an out of sample area, the predicted value under the model. So basically what you do is you take the covariates from that area xi. Okay, so assuming that obviously you have population data, administrative data, geospatial data, or other forms of data for that area, you can use this and you can combine that with the estimated model parameter, which is beta hat, and that will give you an estimate, a synthetic estimate for that out of sample area. And for that also you have an estimator of the mean squared error, so you have an estimator of the synthetic a mean squared error estimator of the synthetic estimator that is given by this expression here. Okay, so I mentioned this because most likely in your application of poverty mapping in Colombia, a number of areas will be out of sample, and I don't want you to go through an exercise and then arrive at that point and not knowing what to do with those areas. So as I said, for out of sample areas, the only thing you can do, I mean, there are multiple things you can do, but the simplest thing we can do is to try and use a set of covariates for these areas and then borrow the model parameters that you have obtained by training the model to the data and then apply that in order to get a synthetic estimator. Obviously, you have to be careful. We had a nice discussion with colleagues. I think it was Santiago and it was also another colleague last week, where we said, what if these areas are very selective areas? So it's areas where we haven't observed anything. They are not left out of the sample based on a random process, but the fact that we don't have data from these areas signals that there is something else going on. Then we have to be very careful about the application of this estimator, because if the missingness effectively of the data there is informative, then making inference about these areas will be a lot more complicated. Okay, so this is assuming that some municipalities are left out, but the reason that these municipalities are left out is not informative effectively, and there are other areas, similar areas, that are observed in the sample. Okay, so this is something to reflect on as you go through the poverty mapping exercise in Colombia. Okay, I'm not going to talk about generalized functions, variance functions too much, because Angela has already covered that. Remember, one thing that I'm going to remind you is that under the Fairhead model that we are going through at the moment, the estimates of the sampling variances of the direct estimates are assumed to be known. So sigma squared EI is assumed to be known. Okay, so and you can do that by obviously calculating direct estimates and the sampling variance of the direct estimates. In some cases, as we will see in an example later in this session, one of the things that we may have to do is to use some smoothing method via generalized variance functions, for example, in order to smooth the estimated variances of the direct estimates. Okay, so there are many ways to do that, but the basic idea is that you need to define a model, such as a regression model, relating the estimated standard errors or the coefficients of variations of the direct estimates to a set of explanatory variables, okay? And the explanatory variables may include functions of the direct estimates and other design characteristics. And what you do is you fit the regression model, and under the model you produce predicted standard errors, okay? And these predicted standard errors will replace the original standard errors estimates. And via this process, effectively, you end up smoothing the variances. So this is the generic idea, but I'm going to describe this in an application to some poverty data a bit later on. So I'm going to describe the use of a GVF, a generalized variance function, later in this session. The other thing you may want to do, and I know that was part of the specification of the curriculum, is you may be interested in benchmarking. So what is benchmarking? So benchmarking means that you want the, if you take the small area estimates within a bigger area, so say we have municipalities, so the idea is effectively to, if you have estimates smaller estimates of municipality, what you can do is you want these estimates of municipality, when they are aggregated out to department, say for example, that they coincide with the estimate, the direct estimate at the higher level. So this is not automatically achieved, but it's a very important property for National Statistical Office. So you want somehow to have consistency as you aggregate the small area estimates from the lower geographical levels to the higher geographical levels. Okay, so what you want to do is you take your eBLAP estimates, theta hat I eBLAP, and you adjust them such that when you sum them up, okay, that the sum of these is equal to a tau. Tau is effectively the estimate, the direct estimate at the higher level. Okay, so these benchmarking procedures are allowed for some numerical consistency. So here is an expression for obtaining benchmarked eBLAPs so that they are respecting the constraint. Okay, and you can do that effectively by taking your eBLAP, the unadjusted eBLAP, and then adding an expression here, right? So this expression may look a bit complicated, but let's go through a bit this expression here. So you have the psi I here, this parameter here, which I use the psi I letter, is equal to the compositions, the ratios of the population in area I over the total population. All right, so that's a kind of weight of the population sizes in area I compared to the total population. Okay, and there is another parameter phi I. Okay, and then we're going to see one particular example where effectively, if you set the phi I also equal to ni over n, then this adjustment will lead to a very simple adjustment, which is called the raking benchmarking method. Okay, so that's a naive way of adjusting the estimates. Okay, and why is it naive? Because effectively each area estimate is adjusted by the same is adjusted by the same factor. Okay, however, you can make more complex adjustments that take into account also the precision of the estimates, like the mean squared error, by modifying this parameter phi I. And there is a paper that summarizes this information that is by Gauri Datta, Mallegos, and Rebecca Sturges and Jerry Maples. It's a paper on Bayesian benchmarking that was published in Test in 2011, but also 3 alternative methods of benchmarking have been incorporated into the R package EMDI that we're going to visit and learn how to use in a moment. Okay, so this is effectively one way of imposing a benchmarking consistency into your eBLABs, and there are different methods you can do that. The simplest method is by using this kind of rating adjustment where every estimate is adjusted by the same factor. Okay. So the other thing I wanted to cover very briefly before we move on to some applications is maybe a Bayesian perspective a bit, because I know that some colleagues might be interested in a Bayesian interpretation of these models. So here I put again up the Fairhead model. So you see that the Fairhead model is defined as by taking the direct estimates, theta hat I direct, given xi, the covariates, beta, ui, the random effect, and the sampling errors. This is assumed to follow a normal distribution with mean xi beta plus ui, which we have denoted as theta I, and a variance sigma squared ei. Okay, so this is effectively the combined model that we have. We also assume that ui, the random effects given depending on number of parameter sigma squared u, that also follows a normal distribution with mean 0 and variance sigma squared u. And the target here under the Bayesian perspective is to obtain posterior estimates of theta I. The theta I parameters are functions of model parameters, so we want to obtain posterior estimates of theta I, and we also want to obtain posterior variances and credible intervals of theta I. So because, as I said, it's point estimates will not be enough. We need also a handle on the uncertainty around these point estimates, and this is provided by the posterior variances and obviously by the credible intervals. So in addition to the likelihood defined under the model, what we need to do here is we need to specify some priors on the model parameters. And in R, you have packages, small area packages, that automatically implement Bayesian estimation. For example, I mentioned the HB SAE package. Alternatively, if you're familiar with writing code in Stan or in JAGS or in BAGS, you will see that R links has an interface with these programming languages, and you can program your model in your own way using, for example, Stan. And in the applications that I'm going to show a bit later, we have done a programming of the Fairhead model in Stan. We use RStan to estimate the model, and then we're going to illustrate the model and compare the Bayesian results to the frequentist results, frequentist fitting of the Fairhead model. Okay, so just to give you an idea, so this is the Fairhead model. We have data. The data is the direct estimates, which you calculate using your survey. You have the covariates xi, and you have the sampling errors, which are estimated using survey techniques, and they are assumed to be known. What is unknown here are my betas and my sigma squared u, so the regression parameters and the between area variability, sigma u. And we need also here in the Bayesian framework to specify priors. And there are different ways to specify priors. Here, what we assume is that sigma u will be parameterized by a precision parameter, which is typical in these cases. So we're going to assume that tau u has a prior that follows a gamma distribution with certain parameters, and beta also we need the prior on beta, and we assume that beta follows a normal distribution with mean 0 and some large variance effectively. So you're pretty we are pretty ignorant about how these betas will look. They have a very large variance effectively. Okay, and we're going to use this specific specification here for the Fairhead model and fit the model in RStan and compare the results to frequentist results obtained via standard packages such as the package EMDI. Okay, so let's get into some action now, some practice. Okay, so I am going to introduce here an R package called EMDI. So this stands for estimating and mapping disaggregated indicators. So that's a package that was written by colleagues of mine, including myself, some time ago, in 2019, I believe, and now it includes also an entire session on area level models. And I have included a link here, and if you click that link, hopefully that will open. Can you see my screen? What I'm seeing now, Angelica?
Yes, I can see your screen.
Do you see the PDF that is there? Yeah.
Yes, a framework.
Yes, that's it. That's the one I wanted to show. So you will see that there is and I have already sent that to you as part of the additional materials. So that is an entire vignette that will tell you exactly how to estimate area level models using the EMDI package in R. Okay, and this is the package I'm going quickly through here. This is the package we will be using in practical applications in order to fit the Fairhead model, but also see some of the extensions of the Fairhead model in practice. Okay, so the dataset that we're going to use is based on an Austrian data. It comes from a survey called the EU SILC, is the European Union Survey of Income and Living Conditions. Okay, and the reason that I'm using this dataset is because it's by default available in the EMDI package. So I have a computer lab 2, that I'm going to send to you. I mean, I'm waiting a bit for Angela to finalize computer lab 1, and then computer lab 1 on direct estimation and model assisted estimation, and computer lab 2 on area level models are going to form the first 2 computer labs for implementing some of these methods in practice. So we're going to be using this Austrian dataset, which is part of the EMDI package. So here I'm describing some of the key operations when you start with the EMDI. Obviously, you load the library, you write library EMDI, and that will load the library, assuming you have already installed it. So the first step is to install EMDI in your R, and then load the library. And then we use a combined dataset. And the combined dataset has two data sources. One is the population data, and the other is the sample data. Okay, so what we assume here, we have a population dataset. In the population dataset, we're going to have all these covariates, xi, which were denoted by xi in my overheads. And these covariates are going to be coming from census or administrative data or other data sources, and are going to be at the area level. And you have also sample data, and the sample data will include a set of direct estimates and also the estimated variances of the direct estimates. Okay, and both datasets will include an identifier, a geographical identifier called domain. That will be, in the case of DANE, the names or the numbers of the municipalities. So both datasets will have to be mapped, merged, using these domain identifiers. So what we can do in order to, say, estimate or start using the Fairhead model, okay? So here what I'm doing is I want to estimate a Fairhead model and save the results into this object called Fairhead_std. By the way, that name on the left-hand side, what I have on the left-hand side here, is arbitrary. You can pick any name that you want. Here I have included something called Fairhead standard model, but you can use a different name. The important aspect here is that in EMDI, the Fairhead model is estimated using function Fairhead. Okay, so if you want to ask EMDI to estimate an area level, the Fairhead model for you, then what you need to do is to use function Fairhead. Okay, what do you need to specify into function Fairhead? You see that the structure here is very close to fitting a regression model in R. Okay, so you need to specify the fixed part of the model. Okay, what is the fixed part of the model? On the left-hand side, you have the direct estimate. So here we want to estimate the mean average equivalized income in Austrian areas, areas in Austria. So mean here are the direct estimates. And then on the right-hand side, after this symbol here, the assign symbol, we have, or the tilde symbol is effectively, you have a set of explanatory variables that are predictive of income, of mean income. So we have the CAS variable, whether someone is self-employed or not, and so on. There are other covariates in the dataset. What else do we need to specify? Remember that under the Fairhead model, you have to assume that the variances of the directs are known, estimated using your survey data, and treated as known. So the var_dir argument is where you have to put the estimates of the variances of the direct estimates, which are here given a name called var_min. Then you have to tell R what is the name of your combined dataset. Okay, here the name of the combined dataset is combined data, but you can use any other name. It's just the name of an object. You have to specify the domain identifier. So what is the domains that you are trying to estimate for, because R needs to know what domains are used for fitting the model and also outputting the point and the mean squared error estimates. You can specify the method. Remember that the method is important for estimating the variance component, so whether this is ML or REML. And then there is a mean squared error argument, where if it's false, then the R will not output any results, but if it's true, then R will try to estimate the mean squared error. And in that case, you need also to specify what type of mean squared error you want. Here, we're using an analytical mean squared error, so R will go and apply the Persadra Estimator and output an analytic mean squared error estimator. But here we can also specify Bootstrap, and we will see examples where Bootstrap is being used to estimate the mean squared error. Okay, so hopefully that will give you an idea about how the Fairhead model is set up in R. Just to give you a bit more detail about how your dataset will look like, if I can find it here, that will be ideal. I'm not sure if this is included in the file here. Let me just have a look. Perhaps not. I'm going quickly through this to see if there is a setup of the dataset here. But if it's not here, then you will see that in Computer Lab 2 is not here. Apologize for this. But we will see when we do Computer Lab 2 exactly how the dataset looks like. Okay, so this is helps you to understand how the Fairhead model is set up. So you have to specify the direct estimates on the left-hand side, the set of covariates on the right-hand side, specify the direct means, specify the name of the dataset, specify the name of the domains, where the domains are saved, and also the method that you want to use and whether you want to use mean squared error estimation, and if yes, then what type of mean squared error estimator you want to use. Right, so let's move on. Model selection. So in EMDI, you can use a function called step, okay? And then you can use a criterion by select which model fits the data best. Okay, so here we are having a we're using the AIC criteria, so the archaic information criteria, but there are other types of criteria you can use in order to select the model. And so here we illustrate the use of the model selection using 3 covariates. Okay, so I'm starting with 3 covariates here, a variable called cash, a variable called self-employment, and then a variable called unemployment benefits. And all of these 3 variables are hopefully predictive of the average equivalized income in regions in Austria. So I say that I want to now, I'm using function step, and I put in function step the object, the Fairhead object, okay? And then I'm using a criteria, and I'm going to do my model selection according to the AIC criterion. So if I let R decide that, okay, you see that in the first iteration, okay, it says that my AIC is minimum when I drop my unemployment benefits variable, okay, and then if I drop the unemployment benefits variable and I run the model, or R will run the model for you using the remaining 2 variables, so cash and self-employed, you see that the minimum mean square, the minimum AIC is when none of these variables are dropped out of the model. Okay, so at the end, out of these 3 variables, we end up with a model comprising 2 predictor variables, variable cash and variable self-employed. Okay, and that is using the AIC criterion. All right, so again, this function will help you to try and, especially if you're using a very large number of covariates, where model selection becomes can become quite tedious to set up. I would say that using the step function as a first approach will be a good way to try and clean or reduce the number of variables that are considered, and then going through the remaining variables in some detail to build your model. Right. So in terms of processing the results, one of the first things you can do after you fit the model is clearly to plot some of the outputs of the model fitting. And if you use the command plot, and then you specify the object where you have saved your area level model results, that one of the outputs that this will produce is QQ plots of the realized residuals and the random effect. And hopefully this should be looking roughly normal. If there are departures from that, then that will signify and signal that perhaps your model assumptions may not hold, and you may want to go back and reconsider the model. In terms of what else you can do, a very useful command that I believe you will find useful if you consider using area level models is to use this command called compare_plot. Okay, and what this does for you is it compares the model-based estimates under the Fairhead model to the direct estimates. Okay, and we can go through this plot in a bit more detail. So the top left-hand side plot, what it does, it's plotting the direct point estimates against the model-based point estimates under the Fairhead model. And ideally, what you want to see is that the dark blue line is very close to the light blue line, because that will indicate a very good consistency between the direct estimates and the model-based estimates. And remember that we want to have our model-based estimates to be close to our direct estimates ideally. Okay. The top right-hand side plot will give you a comparison between the direct and the model-based estimates in terms of ordering the by decreasing mean squared error. Yeah, so you see that on the left-hand side of the plot, direct estimates are having a much higher variance compared to the model-based estimates. But as we move to the right-hand side of the plot, then the both direct and model-based estimates are very close in terms of uncertainty. The bottom left-hand side compares the CVs, okay, of the model-based estimates and the direct estimates, and you can see by using box plots, okay, and you see here that if you look at the top box plot, the light blue box plot, which is, corresponds to the model-based estimates, you can see that overall the model-based estimates seem to have a lower coefficient of variation than the direct estimates in this example. So it's always a good plot to look at in order to see whether the use of a model provides you with some efficiency gains in terms of reducing the uncertainty and in that way reducing the coefficients of variation as a result of using the model. And then the final plot is effectively a plot of CVs, of coefficients of variation, where domains are ordered by increasing CV of the direct, okay? And you see that in most cases, the model-based estimates are below, the CVs of the model-based estimates are below those of the direct estimates, okay? So in this case, the compare plot function can be used in order to do some comparisons between the direct estimates and the model-based estimates, which is really important when you communicate the results and you prepare a poverty assessment or any other kind of report for official purposes. It's very good for those people or those groups and panels, advisory panels that review your work, to be able to have an understanding of how the model, if you use a model, what gains it brings into the estimation process, okay? Right, any questions up to this point? Keep looking at you just in case you have any questions. No, not at this point, okay. In terms of communicating, your results, EMDI will give you quite good tools for extracting and visualizing the estimates. So in order to do that, you can use this function called Estimators, okay? So what you need to specify inside the Estimators again is the name of the object where the results have been saved. And if you specify that the mean squared error is equal to true, that will also output estimates of the mean squared error. Here I'm just outputting the 6 first lines. That's why I'm using command head here to output the first 6 lines of the results. The first thing that you will output is the name of the domain, the name of the area. In your case, that will be a set of municipalities. Then you have point estimates from the direct, okay? Then you have the direct mean squared error. Then the column called Fairhead will give you the model-based estimates under the Fairhead model, and next to it you will get the mean squared error estimates under the Fairhead model. And one additional functionality of EMDI is that you can write these results into an Excel spreadsheet via function write.excel, and you can output that into a separate file if you want to write a report and prepare tables and so on. So by using the write Excel function, these results and additional results will be output into an Excel spreadsheet, and then you can use that to prepare your own tables. One important thing, as I said, is visualization. Now, EMDI is not a GIS software. I mean, EMDI uses some functions that are within R to try and map the results, but you know, there may be better ways to visualize maps and so on via some other more specialized GIS software. Nevertheless, if you are interested in mapping the results, you can do that in EMDI by using function map_plot and then specify the various arguments in there. And there is an example in the computer lab how to do that. Of course, if you want to map the results, obviously you have to have a save file The shapefile for Austria is coming with the EMDI package, but of course, in the case of Dane, there will be a shapefile from Colombia that you can use to map your results. And before I go to the Bayesian framework, I just wanted to also talk about benchmarking. If you want to benchmark your estimates to higher level estimates in order to ensure consistency, as I said, you can do that again with EMDI. You can use this function called benchmark, okay? And then inside there, you can specify the object. You can specify the numerical benchmark that you want. That will depend on what the higher level direct estimate is. You have to specify the share of the population in each area. That, remember, is this parameter called xi, which is the ratio between the population size in area I divided by the total population size. And then the type, you have different types in EMDI. Here we are specifying a raking type method. So that's the simplest possible adjustment you can do to ensure consistency to the higher level benchmarks. And if you do that, then in addition to the direct estimates and the Fairhead estimates, you will get another column, the Fairhead underscore benchmark. And then these benchmark estimates are going to sum up to the value that you have specified. So this is, in this case, is the higher level direct estimate is has an equivalized average income of 20,000 euros, 20,140 euros in Austria. Okay. So, any questions, please? You've been very, very quiet. So, are there any questions? Okay. As I said, I promised that I'm going to give you some results on Bayesian estimation. Okay. So, as I said, you could estimate the Fairhead model within a Bayesian framework, but in this case, you have to specify priors for the regression parameters and for the variance components. So here, what you get out of this Bayesian estimation is posterior distributions of the model parameters, and obviously you can get 95% credible intervals under the Bayesian framework. In this first plot, what we present is posterior distribution of the model parameters. So you will see that here you have the beta 0 is a posterior distribution of the intercept, is a posterior distribution of the coefficient of the first parameter. I think that was CAS. Then you have posterior distribution of the second parameter, beta 2. If I remember correctly, this was an indicator around self-employment. And then you also get a posterior distribution of sigma squared u. Remember that this is parameterized in terms of precision, but this is basically the posterior distribution associated with this model parameter. Okay, and if you compare these results, as you will see in the lab, when we do the lab, you will see that the point estimates where the blue vertical line is are virtually the same as the estimates you get by considering the frequentist framework for fitting the Fairhead model. Okay, what else can you do from here? From the Bayesian results, you can also get posterior distributions of the district mean equivalized income, and also get a 95% credible interval. And here, what I have done is I have plotted the posterior distributions for 3 areas. So area 1, area 78, and area 52. Okay, so say for area 1, you see that the point estimate under this framework is just below 15,000, with credible intervals that go from 13,000 or a bit below 13,000 to about 16,000. Okay, so the nice thing about this framework is that you get automatically, as a result of the estimation process, you can get posterior distributions of theta i's of the target parameters, the parameters that are of interest for small area estimation. And that's very, very important because that is required in any kind of national statistic. So these are the posterior distributions for the 3 areas. Here is a selection of areas. And what I have done here is I have plotted the frequentist versus the Bayesian point estimates and the analytic mean squared error using Persadra versus the posterior variance from the Bayesian fitting. And you can see that these are lining up very well. Okay, so it's just something that we have included. The Bayesian framework is something that we have included because it was part of what colleagues in the United Nations was asking. And we have an example again in R. So we thought that this might be helpful in terms of seeing an example of how a Bayesian estimation framework can be used to fit the area level model. Okay. So what I have done up to now, and is 4:30, so for the last an hour and a half, what we have done is effectively we started with a recap of area level models, and then we went to explain the best linear unbiased predictor. We discussed mean squared error estimator of the blob. We described the concept of the E-blob, where we replace the unknown parameters with estimates of these parameters. And then we focused on the mean squared error estimator of the E-blob, and we presented an analytic mean squared error estimator under the Persadra. And then we moved on to describing an example of parametric bootstrap that will enable you to obtain mean squared error estimates under the Fairhead model of the E-blob under the Fairhead model. We talked about prediction for out of sample areas. We just recapped a bit on generalized variance functions, and there will be some examples. Hopefully Angela is preparing that in Computer Lab 1 to see how this is used. We introduced benchmarking in case you want to have consistency, numerical consistency to direct estimates at some higher level of aggregation, of geographical aggregation. And then we gave a Bayesian perspective on the Fairhead model. And then we started describing how to estimate and set up a Fairhead model in the EMDI package. Okay. We saw how to set it up. We saw something around model selection in the use of the step function to select a model, how to assess the model by using the residual diagnostics and function plot, how to compare the model-based estimates to the direct estimates using the compare plot function, how to extract and visualize estimates and create maps, and then how to use benchmarking in EMDI. Okay, and the final thing is we contrasted the Bayesian results against the frequentist results for the Fairhead model. So what we're going to do for the next sort of 25 minutes or so until 5 o'clock is we are going to extend the basic Fairhead model in certain directions. So we're going to see extensions of that basic model in case these become of interest to colleagues in DANE. And the first one we're going to start with is extending the Fairhead model in order to include what we call spatially correlated random effects. Because remember that until now, we have assumed that the random effects are independent, but occasionally we have applications where areas that are closer or in some kind of neighborhood may be more similar compared to areas that are further apart. And in this case, bringing in this correlation might give some gains in efficiency when we produce the point estimates. And the model that we're going to see is something called a model called the Simultaneous Autoregressive Model, or SAR model. We thought of including this because, again, you may come across something like that, and you may want to consider models that do not assume that the random effects are independent, but you may want to assume a structure around around the random effects, and that kind of structure is trying to capture perhaps some correlation in the random effect. So here is the SAR model. By the way, this is not the only model that you can use to model correlated random effects. There are other models. It's just that this model has been quite popular in some of the literature in small area estimation, so that's why we decided to include it. Okay. So you see that under the SAR model, the combined area level model, okay, what does it do is again linking the direct estimates, theta hat I direct, okay. You need to have well, we have accumulated everything now in a vector, so it's theta hat direct. So this is equal to a set of covariates X transpose times beta. Okay, so that's nothing has changed up to this point. Okay, you also have the sampling errors E, but what is different now is you assume a structure around the random effects U, and this structure depends on what is on a parameter called rho. Okay, so a correlation parameter, and then a matrix W, and the W matrix is a matrix that defines the neighborhood structure or the contiguity structure of the different areas. And there are different ways to define that, okay? And here we're going to look at one particular way of defining the contiguity matrix, okay? So as before, the sampling errors under this model are assumed to be normally distributed with mean zero and a variance matrix R, okay? And the R is in this case the diagonal of the sampling errors, the diagonal matrix, where in the diagonal you have the sampling errors. Then U is also assumed to be normally distributed with mean zero and variance sigma squared U. And V, okay, is given by this expression here. So V is equal to the identity matrix minus rho times W inverse times U, and this is assumed to be normally distributed with mean zero and variance covariance matrix denoted by G, okay? And the expressions for the G variance covariance matrix is given by this expression here, okay? So you see now that the variance covariance matrix G depends on two parameters. It depends on sigma squared U and also on this parameter rho that shows captures the strength of the correlation. The EIs are the estimated variances of the direct estimates, and they are assumed to be known. The W is a spatial weight matrix, okay? And in this example of W that we're going to use here, we use a contiguity matrix where we have non-zero values for areas that are contiguous, that are adjacent. So for neighboring areas, we have a non-zero value, and for areas that are not neighboring, we have a zero value, okay? So this is only one example of that W matrix, and there are different ways of specifying the W matrix. Okay, so under this model, okay, again, assuming that sigma squared U and rho unknown will lead to a best linear unbiased predictor under the Sar model, and estimating these two parameters will lead to an empirical best linear unbiased predictor. And under this model, the SAR model, the E-BLAPs are estimated using this expression here. So theta hat I E-BLAP under this model will have this form here. And you'll see this form is not very different from the form we had before. Remember that the E-BLAP under the standard Fairhead model, if I go back to my expression for a moment, you will see that the E-BLAP, the BLAP and the E-BLAP effectively is basically xi beta hat plus gamma I times this residual here, okay? And under the Sar model, this looks very similar. It's just that this second part has been adjusted to reflect the fact that we assume a particular structure for how the areas are related. So you see the first part is again xi transpose beta hat, and then you have a residual, and then you have an expression here in place for gamma I. Okay, so this is how the eBlob under the Sar model is constructed. And information about this kind of model, for example, can be found in a paper by Alessandra Petrucci and Nicola Salvati in 2006. This is a group in Italy that has done quite a lot of work on spatial correlation type models, especially applied to environmental data sets. Okay, so as with the standard eBlob, we under the SAR model, the simultaneous autoregressive model, we can specify the mean squared error. The mean squared error is again the mean squared error of the blob plus the expected value of the difference, the square difference between the eBlob under the Sar model minus the blob under the Sar model. So basically that's the additional uncertainty that is introduced because of estimating sigma squared u and rho, parameter rho. And again, you can express that as a sum of three terms, G1, G2, G3. And analytical expressions for the first two terms are available. However, the third term here is intractable. So there have been different approximations that have been proposed in the literature, depending on what kind of method you use to estimate sigma squared u and rho. But generally speaking, this third term is a lot more difficult now to estimate. And in order to estimate that, there have been also parametric bootstrap solutions that have been proposed, either fully parametric bootstrap methods or parametric bootstrap solutions for getting an estimate of G3. Okay, now there is a paper that was written by Isabel Molina, Nicola Salvati, and Monica Pratesi again in 2009. That paper specifically focuses on bootstrap for estimating the mean squared error of the spatial eBlob. And it's a paper that was published in Computational Statistics. So let's look at how the parametric bootstrap for the SAR Fairhead model is working. Okay, and again, this is going to be only one of the parametric bootstrap mean squared error estimators that we consider. What you need to do here again is start with your original data, and using your original data, estimate the set of parameters sigma hat u, rho hat, and beta hat. And as with the standard parametric bootstrap we described before for the Fairhead model, what you need to do now is generate a set of random effects, u star. Remember that u star always denotes quantities that are in the bootstrap world. Okay, so we generate a set of bootstrap random effects under the model. So this follows a normal distribution with mean 0 and variance sigma squared u. And then what we need to do is use our bootstrap random effects to construct what we call v star. Remember that v star is up here, right? So it's effectively the identity minus rho times w inverse times u. So once you have u, once you know what type of matrix you use, a special weight matrix you use, and you have rho, the estimated parameter with your original data, then you can create this expression v, this quantity v here. Okay, so I was trying to let your colleague in. So what we are doing here is we are creating, once we have generated the set of random effects in the bootstrap world, then we create a set of v stars. So these are quantities also in the bootstrap world as the identity matrix minus rho hat, where rho hat has been estimated with the original data, times w, which is special weight matrix, inverse, times u star, where u star is the random effect that has been generated with bootstrapped effectively. Okay, So now the third step is independently of U star, we generate a set of bootstrap errors, okay, sampling errors, according to a normal distribution with mean zero and variance R capital. So this R matrix here, remember that's a diagonal matrix. In the diagonal, you have the sampling variances for the different areas. Okay. Once you have V star and E star, you can generate bootstrap values of theta, denoted by theta star, and also generate values of the direct estimates in the bootstrap world by using the model. So the theta hat direct is nothing more than x beta hat plus the V star that has been generated in step 2 plus the E star that has been generated in step 3. And now you have all the data, you have a new set of data sets that you can use that has been generated. It's a bootstrap data set that has been generated under the SAR model, the simultaneous autoregressive model. So we assume that this model holds, and that's an assumption, but we are prepared to make this assumption. And once we make it, then we generate the bootstrap data, and then what we do is we are going to estimate the SAR model using the bootstrap data. Okay. So that comes into step 5. Okay, step 5 effectively tells us to fit the model to the bootstrap data and obtain model estimates under this model. So we compute in step 6 the blob. Okay, remember that the blob assumes that the sigma squared u and rho are equal to the values that have been estimated using the original data. Okay. And then we get an estimate of the E blob, where under the E blob, the sigma squared u and rho, so this set of parameters that is denoted by omega hat, is obtained by the using the data that has been generated as part of the bootstrap. Okay, so that's the difference between omega and omega hat star. The star uses the newly estimated sigma u and rho using the bootstrap data, whereas the omega hat is assuming that the values of sigma u and rho hat, sigma u hat and rho hat are equal to the values that have been estimated with the original sample data that we have. So we have estimates of the blob and the E blob, and then we repeat the steps 2 to 7 a number of times, b times, depending on how many times we want to do that. Normally about 500 times or 250 times might be sufficient for mean squared error estimation. Okay, so one way to estimate the mean squared error is effectively by taking the difference between the E blob that is computed with the bootstrap samples minus the theta hat I star. Okay, in bootstrap B, we run say 500 bootstraps. We take the differences between these quantities over 500 bootstrap replications, we square them, and we divide it by 500, and that will give you one estimator of the mean squared error. That's a fully parametric bootstrap. An alternative way of doing that, an alternative mean squared error that has been proposed in the paper by Molina, Salvati, and Bratesi, is to what we do first is to obtain a bootstrap estimate of G3. Remember that the mean squared error can be expressed in this as a sum of these three terms, G1, G2, G3, and expressions for G1 and G2 are available, but G3 is the more difficult one to estimate. So what colleagues in that, Isabel and Nicola and Monka proposed in this paper is to get, first of all, a bootstrap estimate of G3. What is a bootstrap estimate of G3? Well, remember that G3 is capturing the difference between the blob and the E blob. So how much uncertainty I'm going to introduce by estimating the model parameters, okay? And we can do that. Remember that as part of our bootstrap, we have calculated the theta hat I blob, we have calculated the theta hat I E blob. And so what we can do is just get this difference between the blob and the E-blob. Be careful here. So that's the difference, the square differences between the blob and the E-blob, which captures this part of the uncertainty. So we square these differences and we sum them up and we will divide them by the total number of bootstraps. And then this alternative mean squared error estimator, which we denote by MSE 2, okay, you will see it's given by this term here. So we have expressions for G1 and G2, which we can calculate analytically, okay. Then we add the G3I term that has been estimated under the bootstrap. That's why this has a star here. And then we subtract here the bootstrap estimates of the estimates of G1 and G2 by using the bootstrap replications for estimating the set of parameters sigma, u, and rho. Okay, and so that gives you a bias corrected. So the idea here is that you're using bootstrap to do a bootstrap bias correction on G1 and G2, and then you add a bootstrap estimate of the G3 term. Okay, so here is a bit of combination of using bootstrap to estimate the most difficult bit, which is basically the third component of the mean squared error, and then using analytical terms of G1 and G2, which you bias correct by taking advantage of the bootstrap. So bootstrap is not only used to estimate the mean squared error, but it can be used also to have a correction for bias. And this is exactly what the colleagues who wrote the paper proposed in this case. So that's a second mean squared error estimator that can be used to estimate the E-blob for the SAR model, the simultaneous autoregressive model. The good news is again that the EMDI package has a provision for fitting this model and also has a provision for estimating the mean squared error based on the solutions I just described here as part of this slide on parametric bootstrap. Okay, so what I'm going to do, I think there is only one slide here that I wanted to mention, and that's basically how do we use EMDI, the package EMDI, to fit the simultaneous autoregressive model, the Fairhead model. Okay, so you can do that again by using the function FH, the Fairhead function. The only difference here is that you need to specify the argument correlation, and in that argument correlation you have to put to specify that you want a spatial correlation, so that EMDI knows exactly what kind of model to estimate. Okay, and also you need to specify this kind of proximity matrix, the correlation matrix that is specified here. Okay, once you do that, then you are ready to go. In terms of mean squared error estimation, here we're going to use a parametric bootstrap, which is bias corrected, and it's is referring to the special autoregressive model. Okay, so this is exactly the parametric bootstrap, is the mean squared error estimator 2 I described in my previous slide. And you see, because we're using a bootstrap, here I have specified that I want 50 replications. Obviously, in a real application, it's prudent to specify a much higher number of bootstraps, maybe 500 or 1,000, to make sure that we have enough replicates to capture the estimation of the mean squared error. The first bits here will tell you how to set up a list of neighbors. Remember that what is important to do here before you fit this model, you will have to specify the W matrix. The W matrix is something you as the analyst has to do. Okay, and in the example that I have included here, the W matrix is defined by using this command called nb2mat. Okay, that is what computes a weights matrix. Okay, and the style argument produces what we call a row standardized proximity matrix that will give you the weights for contiguous areas. And in order to do that, obviously you need to use the first function, which generates a list of neighbors that share the same boundaries. Because remember, that under this model we're assuming that there is some correlation between neighbors or areas, municipalities in the case of Dane, that have joint boundaries with other municipalities. Okay, so this is effectively what is done here. Once you have specified this matrix in this example is saved in this object called EU Silk proximity, and then this is what goes into the correlation matrix. And once you specify that in the correlation matrix, then R knows how W is defined. It knows that what you want is to specify a special correlation, a Sar model, and then you have everything ready to set up in order to go ahead with your estimation. Okay, so on that note, it's just past 5 o'clock. I'm going to stop here because then we started a completely different topic. Okay, it's not a lot more that we have in terms of the area level models. One thing that we're going to do is talk about the Fairhead model with transformations, and that's important because one of your colleagues asked on Friday, what happens if we model, say, something like a proportion, say the proportion of households below the poverty line in a municipality, and so transformations may be helpful in those cases. And then I have another extension of the Fairhead model if you want to include covariate measurement error, and that's an important extension as well in case you have multiple data sources. And in Dane, that might be the case, and we thought that this might be a helpful extension to include as part of this the description of area level models. And once we do that, then we're going to cover a case study of poverty estimation in Bangladesh using area level models, and that will conclude our use of area level models before then moving on to unit level models and poverty mapping methods, which might be also the methods that might be more likely used by Dane. However, please do not ignore completely area level models, because area level models can provide a set of estimates, if used correctly, can provide a set of estimates that can guide you, can be an intermediate stepping stone, moving from direct estimates to unit level models and poverty mapping methods. Area level models might be a stepping stone that will provide a helpful and useful, hopefully, set of estimates for you to use in your poverty assessment. And on that note, I'm going to stop the session today.